From Roman times right up to the 18th century, the big problem with ironworking was that of bulk transport. So iron smelting developed where there was iron ore on site and where the other resource they needed was plentiful too. There's been a charcoal industry here for 2,000 years. I'm in the Weald in southeast England, and in the kilns behind me, they're making charcoal. By restricting the air, they can drive off steam and other volatile gases without burning the carbon away.
And the charcoal is almost 100% carbon, ideal for making iron, and it's still used today for making specialized steel. The carbon will react chemically with the iron ore, taking the oxygen out of the iron oxide and leaving crude iron. Air must be blasted in to generate high temperature, and limestone added to combine chemically with clay minerals in the ore. The product, a molten slag, separates from the molten iron and floats on top.
As ever, the expansion of the iron industry was linked to demand, and demand in the Tudor times was for guns. This magnificent cannon was made for Henry VIII and is made of iron plates bonded together with hoops of wrought iron, but the ball it fired was cast iron.
Wrought iron is very pliable and bends easily. Cast iron, as its name suggests, is simply furnace metal poured into a mold. Its properties are very different. However, even a brittle metal has its uses. These are Elizabethan firebacks. In its heyday, there were over 70 ironworks in the Weald. But by 1700, local wood supplies became exhausted, and iron production eventually ceased.
If there's any one place that could boast that the Industrial Revolution started here, it would be the Iron Bridge Gorge in the West Midlands. The River Severn behind me was the M1 of the 18th century, and it transported coal and industrial goods from the north right down towards Bristol. And upriver there, streams cut through the coal measures sequence at Coalbrookdale, and there was already an iron industry in existence in 1708 when Abraham Darby came up from Bristol to rent an iron furnace.
By then, wood was in short supply, but coal was plentiful. So Darby developed a process that turned coal into coke. He then smelted iron using this coke and developed a whole business making cheap pots and pans for the public.
It was the resources that Darby came to Coalbrookdale for. In one rock sequence, he had coal, sweet, low-sulfur coal that coked easily, and he had iron carbonate nodules that had sufficient phosphorus in them to make the iron flow from the furnace, but not so much that made it brittle. And between the two, there were clays, which were heat-resistant, and he could use to line his furnaces.
The business grew, and so did the blast furnaces. By 1777, Abraham Darby III had conceived of the 18th century's biggest civil engineering project.
The first of its kind, a cast iron bridge, opened for traffic in 1781. But despite all the publicity that this brought for the novel material, actually building bridges in it wasn't a good idea. The Tay Railway Bridge collapsed in a storm when the girders failed, and a train and all its passengers fell into the River Tay. This disaster horrified the public, every bit as much as the building of this bridge had impressed them 100 years earlier.
Look closely, and you can see that the girder has snapped where tensile forces were at play. It broke because of impurities in the metal. The fracture of the cast iron supports was the primary cause of the Tay Bridge disaster. The alternative was to use wrought iron where the impurities are removed. Cast iron from the blast furnace was remelted and then agitated to oxidize out impurities such as carbon, silicon and phosphorus, and remove them in the form of waste gases and liquid slags. This was done by puddling the iron. Some of the slag is run off, but some needs to be driven out with the steam hammer. Even so, thousands of strands of slag remain and become threaded throughout the iron. It's this fibrous nature of wrought iron which gives it its great strength and resistance to fracture. Rolling finishes off the process. In 1856, Henry Bessemer patented a process which at first sight does the craziest thing: blowing air through molten iron to oxidize the impurities. Fortunately, all these burn off during the 20-minute blow, with only partial oxidation of the metal. So, at the end, iron containing carbon is added to reduce the oxidized iron back to the metal in a reaction more reminiscent of what goes on in the blast furnace. The final product was a form of iron with greater toughness and elasticity. This high-performance iron was called steel. From the mid-1860s, the Bessemer converter had to contend with an alternative process for the bulk production of steel, which was to become predominant in the first half of the 20th century, the Siemens open hearth process. By using a mixture of hot coal gas and air, the steel can be kept molten for hours and the impurities slowly oxidized. In this open hearth process, scrap iron and steel can be used, and there's less of a problem with phosphorus. In contrast, Bessemer steel can only be made from iron ores with a low phosphorus content.
But the rapid expansion of industry throughout the 19th century was controlled not by the quality of iron ore, but by the availability of coal. Industry expanded wherever coal was to be found.
There were dozens of small family concerns, separately owned smelting, foundry and steel-making works in the old industrial areas, locations which made less sense 50 years on, when steel was best made in large works near the cheapest ore. In South Wales, most blast furnaces were in the coalfields on sites of limited potential. The local iron ore was used up, and ore imported from Spain now had to be railed up the valleys from Cardiff or Newport docks. Coke ovens could still use local coal, but like other works, they were small, antiquated and wasteful. The average blast furnace was only a third as big as those in the United States.
Especially in Scotland, we were very backward because the old Scottish way of making iron, which had been terribly successful in the latter part of the 19th century, was based on using heavy coal as opposed to coking coal. And the result was that a furnace using that type of fuel could only produce 60, 70, 80 tons of iron a day.
On the continent, it was a different story. Each German steelworker could produce half as much again as his British equivalent. After the Great War, German firms had re-equipped and reorganized into combines and were protected by tariffs.
They measured everything. They measured blast furnace gas. They analyzed the blast furnace gas and found out how much carbon in it. Then they checked that against the amount of carbon put into the blast furnace to make sure that it all added up. It was this scientific approach.
And what was our approach to competition along these lines? We introduced tariff barriers too. 1934.
In 2 years, the tariff has reduced imports of foreign iron and steel by 2/3. As a result, these chimneys, which had been smokeless for years, are now belching smoke. Great furnaces such as these are again in full blast.
But they were still the same old furnaces, and government feared that with steel protected, the old inefficiency would continue. So the companies were told they had to re-equip or they'd lose the tariff. The most radical advice came from an American firm of consultants. They recommended that old works should be run down and that all steelmaking concentrated at 6 new sites around the country where raw material costs were lowest. Only one such bold scheme was carried through in the early 30s. At Corby, in the fields of Northamptonshire, there were newly developed open-cast mines which offered some of the cheapest low-grade ore in Europe. In 1942, the Northamptonshire ironstone yielded 10.5 million tonnes of steel. In the 1970s, 3 million tonnes. In 1980, Corby Steelworks closed. The Northamptonshire iron ore had become too expensive to use compared with the importation of higher-grade ores in bulk carriers from abroad. Reserves left in the Northamptonshire ironstone had been estimated at 1 billion tonnes. It's a story repeated many times. A century of steelmaking was celebrated by Scunthorpe in 1990. Sitting on the Frodingham ironstone, another Jurassic iron-rich deposit, the industry developed here because of the proximity of local ore.
The worked area of this ore body is about 15 kilometres long and about 10 kilometres wide, and the ironstone itself is about 10 metres thick. And we can tell by these layers and the features within the layers that these rocks were deposited in shallow water. And we know it was the sea because it's teeming with marine fossils. This ore contains between 18% and 26% iron, and it served the iron industry here in Scunthorpe for over 100 years. And they stopped working this quarry in 1988, not because it was exhausted, but incredibly because it became more economic and more efficient to import the ore from places as far afield as Australia.
After the Second World War, consumerism took off as never before. Iron and steel couldn't be produced fast enough in the 50s. To control the industry, there was nationalisation, denationalisation and renationalisation. But by the time the British Steel Corporation was formed in 1967, demand was beginning to slacken off. The response of BSC was to imitate the style of successful industries abroad, notably Japan. By opening entirely new steelworks, the Japanese had increased their output 10 times over since the war.
I think the thing which impressed me most was the scale on which modern steelmaking has to be operated to be successful. The Japanese had blast furnaces which didn't make any less than 10,000 tons a day. Now, in our case, the largest blast furnace we have made only 2,750 tons per day.
The expenditure on environmental control must have been colossal. They didn't just spend it on trying to get as much tonnage out of the furnace as possible. They spent their money in Japan on making sure that the men were working in good environmental conditions.
Japanese style of steelmaking was the aim of the full development plan that the corporation finally published in 1973. Steelmaking would be rationalised into 5 major works, just as argued in the past. The biggest new works would be built at Redcar on Teesside.
On the south bank of the Tees estuary, the first stage of the giant Redcar development is already finished and working. The port through which millions of tons of iron ore arrive from all over the world is at one end of the 2,000-acre site. It can handle these supercarriers, 100,000 tons and over, which bring down transport costs so radically.
Japan was in the middle of its big expansion, and they were of necessity building these large coastal sites. They had nowhere else in Japan to build them. They had this enormously growing domestic market in Japan, a very big regional market in Southeast Asia, and their scale of operations were totally different from ours.
Nevertheless, the Japanese idea caught on. A deep water harbour at Port Talbot was developed to receive the cheapest ore from anywhere in the world. But hand in hand with the availability of cheaper ore went rationalisation. 80 kilometres away, the new Llanwern steelworks had been built with everything on site, including coke production, iron smelting, steel making, and sheet and coil forging. Since they were bought in, the raw materials could be precisely related to demand, so no wastage. To show you some of the advantages of rationalisation, we'll concentrate on making iron.
This is the first part of the steel-making process, where the ores and other materials are blended behind me here. Now, there are three ingredients in the blending. The first is the iron ore itself. The iron ore is imported from Australia, from South Africa, and from Scandinavia, and it has a content of iron of about 60%, much higher than we saw at Scunthorpe. And that's being added together with other metalliferous material, which is increasing and producing the right trace element chemistry for the steel. And into the blend also goes limestone and coke, both of which are needed to make the chemistry of the blast furnace work correctly.
In the coke ovens, coal is heated to 1300 degrees centigrade. The heat drives off water and volatiles and turns coal, with about 65% carbon content, to coke, which is 99% carbon. Filters control atmospheric pollution, so ideally there are no emissions other than steam from the water used to quench the coke and stop the chemical reaction you don't want at this stage, its oxidation in air.
In chemical terms, the job of the blast furnace is to get enough carbon and enough energy close to the iron oxide so that it can reduce it from iron oxide to iron. Now, most of the carbon comes in the form of coke, but in addition to that, there's carbon in gas form. There's gas recycled from the blast furnace itself, there's gas that comes in from other parts of the steel making process, there's gas from the coke ovens, and there's even gas coming in the form of natural gas from outside the plant. And even that's not enough carbon. They have to inject oil into the blast furnace as well. Now, the great rationalisation here at Llanwern means that all those sources of gas are readily available and close to hand, so they can be got to the blast furnace as and when they're needed. The products of the blast furnace, besides the iron, include this. This is slag. Now, it's formed from the chemical reaction of the limestone with the silicates in the iron ore. And in the old days, it was just a waste product, tipped into unsightly slag heaps. Now, resources all have a use wherever possible. This is used as hardcore, it's used to make tarmac, and most recently, it's used to make concrete, because slag concrete is resistant to alkali and seawater attack.
In the 1950s, before the steelworks was built, this was a natural marshy area. When they built the plant, they knew they had to do something with the wastewater from the coke ovens.
And this is their solution. It's a huge area of reeds, and the reeds are purifying and cleansing the water and getting rid of all the chemical impurities from it. They concentrated the reeds here, and this is as much part of the steelworks as the view behind me is.
Many other aspects of steel production are rationalised at Llanwern. They recycle many things. They could do more. They could recycle all their heat and all their water within the site. But to do that efficiently would require pulling all this down and building a new steelworks, and that's not economic. Introducing new technology has always caused problems for the industry. In 1967, when the newly formed British Steel Corporation inherited Britain's 41 steelworks, open hearth furnaces were standard practice. Abroad, though, the basic oxygen system, BOS, was used, and steel made this way was far cheaper. Oxidation of the impurities is much more efficient, using oxygen gas introduced into the melt through a water-cooled pipe called a lance. To adopt this technique meant that the steelworks using open hearth furnaces had to go. Earlham, near Manchester, became the first steelworks to close since the 1930s. 4,000 were made redundant. British steel was expensive as the recession struck. Demand was collapsing in the mid-70s when the whole BSC plan had rested on their own forecast that it would go on rising. With higher energy prices, the old works not on the BOS system cost more to keep going.
Glengarnock, Hartlepool, Shotton, Corby, Bilston, Shelton, Ebbw Vale, East Moors in Cardiff. Seemed every week there was a plant was closing down. Men were getting disillusioned. People were afraid that, well, were we going to be the next one?
It's doing you no good. It's doing the
1980 saw the first national steel strike for 70 years. Unexpectedly bitter, it lasted 13 weeks. After the settlement, the nationalised industry was told to move even faster with closures and redundancies. Steelmaking was never restarted at Coulby. 6,000 steelworkers lost their jobs. The greatest showplace of the 30s was closed. Its inland ore was now too expensive. At Ebbw Vale, the cost of transporting materials to the plant in this Welsh valley finally proved too high, and 5,000 were redundant. Shotton closed too. Between 1973 and 1980, over 170,000 workers lost their jobs. Since then, another 100,000. Despite all this attrition, there is still world overcapacity in steel production and a global steel mountain. Supply still exceeds demand.
The fate of the modern steel industry, it's closely linked to the industry that creates most of its demand, car manufacturing. But even that's changing. All the bodywork on a car like this, the Renault Espace, is made of a composite of glass fibre and polymer. It resists shocks more easily, and it won't corrode, even in sea air like this. Plastic components are increasingly being substituted for steel ones in the engine, and even the chassis and body frame might be composed of non-ferrous materials too. But there are problems. Just how do we recycle this stuff? And the answer at present is with difficulty. For example, just imagine the problem of sorting out all the different types of plastics used in a car. So is the substitution of materials a real advantage or just fashionable?
Plastic cars or steel battleships? What dictates the fate of an industry has always been the demand for its products. Up to now, expanding technology, substitution, or even fashion have influenced the way the resource is exploited. In the future, we may not have the luxury of being able to use up resources in such a way. And even the steel industry, big as it is worldwide, will continue to be influenced by the ups and downs of changing fortune.